Willkommen, bienvenue, and welcome back to Scrap Mechanic with Lyte. What? Got something on my face? Yeah, so I went a little ham-bone with the paint gun. Might have got a little on myself. I've been meaning to make a skin for a while. It's a first draft. I'm okay with how it kind of turned out. A couple things I'd like to do better. The hair, yeah, definitely want to do the hair better. It's just, I like how fiery it is, but it just doesn't quite look right. I like how the eyebrows turned out, but the rest of the hair, needs more work. I like my icon on the headband. Love the color of the jacket. That deep, rich purple turned out really nice. I don't have a lot of experience working with 3D meshes, so I doubt I'll be doing any serious, cosmetic surgery to change my bone structure, but we'll see. But that's not why you came here today. You came here for Newton's laws and perpetual motion. So, you likely know Newton's 3 laws of motion, but if you don't, we'll go through them anyway. And we might not do them in the order they're presented in the 3 laws sort of format, because it's easier to start with the third one. Every action has an equal and opposite reaction. So we turn to the right, green goes right, red goes left. We turn to the left, the opposite happens. Now, you might be thinking, oh, Lyte, you just put 2 bearings there and put them in opposite directions. Well, no. There are 2 bearings, all right, but only the middle one is powered. And we're using left and right, not forward and back. There's no engines. That's just turning left and right. So, nice and attached, nice and simple. Demonstration of when you try to turn this guy to the right, well, that torque is countered on the bottom. This happens both with torques and with other sorts of forces. So, if you've ever been on a boat at a pier that isn't necessarily tied down tightly, you go to step off the boat, and the boat tries to run away. You're trying to go this way, pushing down on it, pushed it the other way. Equal and opposite. But that, again, is forces. Which would bring us over here for Newton's second law, which will be demonstrated in this section. But before we get there, I just wanted to show you, this is how it works with the turning. Here's how it works with the electric on the lowest setting. It's just nice and easy. The same setup, free spinning, powered. It goes in opposite directions. Now over here, we've got gas, also on its lowest setting. Keep that in mind. Lowest setting. It goes all wobbly and mad. Just with 4 pieces of wood on its lowest setting. Yeah. It's a little weird. So, that's Newton's third law. Action, reaction, equal, and opposite. Here, we've got his second law. That's that the force is equal to the mass times the acceleration. So this first one doesn't really show you anything. This is still part of the third law. This is just set up with a controller, 360, loop, slow. Again, power the middle, leave the bottom free spinning, equal and opposite. Brilliant. When you turn it off, it tries to reset back to where it started. That's just the nature of a controller. Over here, it might be a little difficult for you to tell due to the paint job, but this top bit is stone. So we've got concrete, wood, and metal. So stone has more mass because of its higher density. So if we hit this, how do you expect it to move? Should they move equally and oppositely? Well, no, because this has more mass. So the wood spins more freely than the stone. Now, theoretically, it should be double, because the stone has twice as much mass as the wood, which we figured out from our various measurements. But as you can see, it's not quite lining up evenly. So there might be other forces at work here. But the general idea of the more massive something is, the harder it is to accelerate, still seems to hold. And we could do further investigation to see just how differently they rotate. Could be interesting. And here with metal, we find something interesting. The metal just stops. Instead of being very, very slow versus the wood, it reaches some sleep period where it's just like, it's not worth moving anymore. Just let the other thing spin. There's probably a good programming reason for it, but it does lead to some weird calculations. But it might come in handy to be able to have something that should be free spinning not move at all. And that starting and ending little oomph is also a little disconcerting. But that's a whole other story for a whole other day. And then Newton's first law is that uniform motion will continue unless acted on by an outside force. That also means it'll remain uniform motion until forces become unbalanced. So if we turn this guy on, this block here will stop it from moving. Because once it starts going, boom, you now have two balanced forces. One of them pushing around this way, and the other pushing around that way, equal and opposite. Thus, the total force is zero. It goes nowhere. This is how things should work. Now I say should, because over here we've got some things that don't work that way. When you've got this set up, no matter what was between them, this should not rotate. You have balanced forces on both sides, which leads to no further motion. Now, if I were to hit this with a hammer, it should move. Because this is free spinning. So if I hit it with a hammer, that thing should spin. For example, 1, 2, 3, bearing, thing. It should kind of spin. Oops. Like that. Even better. Let's put this here. Attach this. It's too many, isn't it? Okay, like that. Let's throw a controller on it. And we want to send it blue, I don't know, just a little bit less than 90 degrees. Let's throw it to 75 and see how good it is. That's too far. We want it just barely touching. Okay, so we've got the thing just barely touching, just like that. And then we hit it, and it just spins around. That is what this should do. But it doesn't. It's an interesting phenomenon. Physics speaking, it should be the same as this, but it's not. There's something else going on here with the collisions. And, consequently, there are other interesting things that can happen. For example, here is the standard suspension glitch. You've got a suspension into a block, which will try to spin into this block, which should result in this sort of action. But it does something entirely different. And note, I've turned it off. It's trying to reset back to normal. It may or may not be able to. Okay, there we are. And if we hit it, it's fine. But also note how misaligned this block gets once it starts moving. Blocks are not particularly strongly attached to suspensions, and thus when it comes together, instead of colliding like this, it pushes out of the way and eventually starts to compress the suspension, and the suspension itself is a little bit weird. So that's the basic suspension glitch. It pushes into it, and instead of stopping like this or even getting all weird, it pushes it even harder. So it goes in the direction that the green pushes into the red. Now, this you could blame on the suspension or the bearing. Either one could be causing the problem. Maybe the bearing is over-rotating it, like over here, doing something weird. Boink. So let's see what happens if we take the bearings out of the axis of rotation. So here, it's rotating in the same axis as the free spinning one. Here, we have a free spinning bearing here. The other three bearings for this compression are not in the same axis. They're going this way as opposed to that way. So now, we push the button. It moves a little. Might just be a residual sort of issue. It seems to be okay. But you knew there had to be a but. Let's take it up to 44, I think. And then try it again. And there it goes. So here we are. We have a spring doing some interesting things. The bearings are no longer in the same axis, so they shouldn't be able to rotate it. But again, there are bearings here, and they are starting to become stressed. You can see them sticking out a bit from the pipes. So it could still be the bearing that's causing the problem. It could be the suspension. But if you think that this is normal behavior, take a spring in your hand and just squeeze it between your two fingers. Thumb and index, thumb and whichever. You can do that for as long as your muscles in your fingers hold out. But you don't feel any pull on your wrist, on your shoulder, only gravity. If you're compressing a spring like you're compressing this one, the only force necessary is from the pinching. It doesn't try to rotate anything else. So something around here is doing something odd. But there is power here. There is a continuous source of power, so it's feasible that if something is odd, you might be able to get perpetual motion because of the input of power. Now, here, there is no power. We have a free spinning bearing and two suspensions and a bit of metal. That's it. And we take our hammer and we hit it this way. Does a whole lot of nothing. You just hit it and it moves a little. Nice normal reaction. What you would expect from this sort of thing. It's kind of heavy, so it's kind of hard to get it moving. And then you hit it the other way. And it just spins and spins and spins and spins. No input of energy aside from just getting it moving with the hammer, which we showed going the other direction. It barely did anything. I mean, with these guys, you hit it, and it slows down. Now, you'd think that Aristotle's method might have been right, where the velocity is equal to the force times, or the force equals the velocity times the mass. That adding the force is what makes things move. And when you remove the force, they stop moving. Oh, that's weird. You remove the force, they stop moving. But Aristotle didn't necessarily have access to all of the wide range of forces that can be acting on things. Ooh, that was weird. So there's friction, there's air resistance, there's all sorts of forces acting on things all the time. So it's not just you hit it and it moves, you stop hitting it and it stops moving. It's you hit it and it starts moving. It wants to keep moving that way. It really does. But it can't because of friction, because of the air, because of something. It just can't keep going. Now, that's real world. This isn't the real world, this is scrap mechanic. It might have Aristotelian sorts of physics. It might be that there's no bonus force, there's no anything else. There is no friction, there's no air. And it really is, you add power, and it starts moving, and then it's just time that makes it stop. Stuff worth testing. But what we can see is that, well, there's certain things that just don't quite follow. And we can make this thing stop. If we get in the way, we can make it stop. And then it's balanced again, and it stops moving. You unbalance it. Ooh, wrong way. Come on, now. And it starts going. So the most likely explanation is that there is something in the way the springs calculate how much to push back, that it ends up pushing itself more than it gets pushed, and breaks the third law. So breaking Newton's third law, action equals reaction, it ends up reacting harder than it acts. Or it acts harder than it was acted upon, one way or the other, and ends up accelerating itself until it balances out the force of slowing down. These are bad examples. The force of slowing down. So normally it would slow down, but since it has added force from the springs, it keeps accelerating until it reaches an equilibrium with the slowing down force. Whether it's friction or air or time or anything, it rebalances itself out at this speed, which is why it always gets to this speed and doesn't just keep getting faster and faster and faster and faster. So that's the paint gun. That's perpetual motion. You can kind of use this for certain things, but I'm not sure how much utility you're going to get out of it. But who knows? You might be super creative and find a way. I've got a contraption planned that'll use this. Not sure how useful it'll be, but it'll be a contraption, and I like it. Hope y'all are enjoying this paint gun. It is really, really quite fun. I don't know if they added it to the book, but basically you hit Q and choose a color. Let's choose this one. And then you click to paint, right-click to unpaint, and you can make nice parquet flooring in an instant. Oops. Or just destroy everything. So, that's all for this episode. I plan on doing one on torque very soon. I know I keep saying that, but I have an idea for testing the torque, maybe not numerically, but at least figuring a few things out. But I will see you in the next episode of Scrap Mechanic with Lyte.